Bismillahirrahmanirrahim. Lecture number three. Uh, and lecture number three, we'll be trying to improve the efficiency of the vapor power cycle a little bit more now. Uh, if you imagine, like in a previous lecture, uh, we were trying to improve the efficiency of the Rankine cycle, and that was improving the efficiency of the Rankine cycle and comparing it with the Carnot cycle. Uh, the mean temperature at which the heat is supplied in the Carnot cycle is much better than the mean temperature at which the heat is supplied in the Rankine cycle. That's why the efficiency of the Carnot cycle is more than the efficiency of the Rankine cycle. We try to improve the efficiency of the vapor power cycle, the Rankine cycle, by two of the basic cycles, and that was the superheat cycle and the reheat cycle. There is another common method or common way of increasing the thermal efficiency of the vapor power plant, and that is through regenerative feed water heating, or simply we call it as a regeneration. In a simple Rankine cycle, if you can imagine, like heat is added to the working fluid at much lower temperature, and that is at the exit of the pump or inlet of the boiler, we would call it. Uh, Thus, we would try to improve the efficiency by increasing this temperature. And if we have increased this temperature, the thermal efficiency of the Rankine cycle will improve. There are different methods of improving the efficiency or increasing the temperature at which the heat is supplied in a boiler. Uh, if you can imagine, like the state 4 is at the exit of the pump or an inlet of the boiler anyway. So we have to compress, if we can compress the feed water which is coming from state 3 in a pump, and then obviously it is actually compressed isentropically. So if we can compress the feed water isentropically to much higher temperature, as in the Carnot cycle, there would be extremely high pressure, and obviously there would be improved efficiency. There would be obviously the 0.4 will be actually increase, and there would be temperature increase, and F thermal efficiency would be increase. So this kind of a improvement, or this kind of a isentropic compression, is not normally possible, or it is definitely you would need a very high kind of a pressure to increase the pressure of the compressed liquid anyway. So if you can imagine, like we left the liquid at state 4, it was already compressed, and compressing a little bit more of the liquid would require more power, pump power, and obviously the efficiency would definitely not increase. And even if it might not be possible to compress water at such a high pressure. There's another method, like if you can imagine the maximum amount of heat, which is actually the maximum amount of heat which is expending is actually in a steam turbine. So that's the maximum amount of enthalpy which is actually expending in steam turbine. So that if I would say, like we are expanding from H1 to H2, so this is the maximum amount of heat as well, which the cycle is losing, or which the cycle is actually going through. So if we can, in somehow, if we can capture this amount of heat, or if we can harness this amount of heat, and amount of heat from the turbine, and then put this heat into the uh, state number 4, if I would say, then the efficiency of the turbine, or the efficiency of the cycle would increase. What I mean to say, like the maximum amount of heat is expanding in a turbine, a maximum amount of the enthalpy is expanding in a turbine. If it is possible to have a heat exchanger which actually surround from the turbine, and we can get some of the heat which is actually expanding in a turbine, and then putting that heat which was in a turbine into the feed water which is going from state number 4, then in that case we will raise the temperature of state number 4, and by increasing the temperature at state number 4 we will increase the thermal efficiency. But there are two difficulties. First, it is difficult to design such a heat exchange, which we would be actually building around the turbine periphery. So that would be definitely a little bit difficult. And even if we do so, there would be increase in a moisture content of the steam at the final stage of the turbine. So already, if it is actually expanding from state one enthalpy H1 to H2, and we have taken some of the enthalpy out of the system, so obviously there will be obviously when it is expanded as state number two, there will be less amount of heat and there will be increased amount of moisture. So practically, this kind of a solution is not possible in a Rankine cycle. However, this kind of a solution, or this kind of a regeneration, or this is called as regeneration. This kind of a regeneration is possible in a Stirling cycle, but the working fluid in a Stirling cycle is normally gas, so it is possible in a gas turbine or a gas periphery rather than the steam one. Then there is another practical solution of it as well, or practical regeneration, we will call it. Again, if I'm saying like steam is expanding from state one to state two, and the maximum enthalpy drop in a Rankine cycle is from state number one to state number two, and that is steam expanding. So in a practical regeneration, uh, when steam is expended in a steam is expanded from state number one to state number two, some of the steam some of the steam is bleeded out, or some of the steam is taken out at some of the at particular I would say like state, and that is mixed with the feed water. So if I'm saying like if I'm expanding from state number one to state number two, some of the steam is actually taken out from the turbine, and it is actually mixed with the feed water heat. Mixed with the feed water. Uh, this kind of a solution, or this kind of the thing, we call it as a feed water heating, and by doing so, the temperature of the steam is actually increased. So the practical regenerative process in a steam power plant is accompanied by bleeding some of the steam from the turbine at a various point. This steam is used to heat the feed water, which is coming from 3 to 4. The device where the feed water is heated is called as a regenerator, or normally we would call it as a feed water heater. This is actually a practical solution of a regeneration, or it is actually a practical solution from which the temperature at the exit of the core, or exit of the turbine, exit of the pump, is actually increased from this point to further to the higher point. So normally regeneration, it's also improve the efficiency, and it also provide the convenient mean of deaerating the water. It is normally the removing of the air that is leak into the condenser to prevent the corrosion in the boiler. Um, discuss this later on to introduce the principle. We will discuss it in a later on thing, but let's introduce the feed water heater as well first. Feed water heater is basically a heat exchanger where heat is transferred from the steam into the feed water. There will be two different methods of mixing, two different method of heat transfer. Either the fluid would be mixed, that what we call it as an open feed water, or either the fluid will not be mixed, that what we call it as a closed feed water heater. In a start, we will be discussing the open feed water heater. This is the schematic diagram of a vapor power cycle with one open feed water heater. So an open feed water heater is a direct contact type of a heat exchanger in which the steam at different temperature mixes. So there is a mixture of a steam and water directly. So both of them are mixing directly. So let's start with the schematic diagram. So let's say like we start with the state one, and that is actually at the inlet of the first stage of the turbine. So in the first stage of the turbine, we would let the steam expand from state 1 to state number 2. At state number 2, we will take or we will bleed some of the steam out of the system. Now let me call it for a start why, and I would explain what we call it, why we call it this thing. So from state 1 to 2, the steam is expended, and at state number 2, some of the steam is bleeded out, and the rest of the steam is expended to the state number 3. Now, at state number 3, which means like the rest of the steam was expended, it is further sent to the condenser where it is actually condensed and at number state number 4, and from the 4 it is actually pressurized to state number 5 using a. Now the steam which is coming from state number 2 and the steam which is coming or the feed water, what we call it, the feed water, which is after the pump, which is coming from the pump exit of the pump at state number 5, it is both mixed in a heat exchanger, and we call that heat exchanger as open feed water heater. So that means like the steam which is bleeded out at state number 2, steam over here, and the feed water which is coming from state number 5 is mixed in an open feed water heater at this point. Now the steam will actually transfer its energy, total energy, to the feed water, and the steam itself will be changing its phase from steam to water, and the temperature of the water at state number 5 was initially will increase. So at the exit of state number 6, we will be having a steam which, oh, sorry, we will be having a feed water which will be having a high temperature than the feed water which was coming at state number 5. Now we have got again a saturated water at state number 6. Now we will be using another pump, and we will be having another pressurizing the feed water from state number 6 to state number 7. Now state number 7 itself is inlet of the boiler, and we would be transferring heat into the from the boiler to the feed water from 7 to 1. So this is what we call it as a regenerative vapor power cycle. Let me do it again, so that's a little bit more easy to understand. So at the inlet of the turbine, we have got steam. The steam is expended at the first stage of this turbine. Some of the steam is bleeded out at state number 2, and it is directed to open feed water heater. The rest of the steam is expended to the second stage, and it is exiting the second stage of the turbine at state number 3. Now, from the steam which is exiting at state number 3 is actually directed towards the condenser, and it is actually condensed from 3 to 4, and we are having a condensed liquid or feed water at state number 4. Now, this water, this condensate, is pumped from 4 to 5, and we are having a pressurized feed water at state number 5. Now, the steam which is coming at state from at 2 is mixed with the water which is coming, feed water which is coming from the exit of the pump in an open feed water heater. The heat will be transferred from the steam to the open feed water, and the temperature of the feed water will rise while the phase of the steam will be changing. So at the exit of the open feed water heater, we will be high temperature feed water. Now this feed water, when we exiting the open feed water heater, is again in a saturated state. And so again, we will be using a pump, which will be pumping this feed water from 6 to 7. Now we are at the exit of the pump and inlet of the boiler. So that means like we would be transferring or we will be generating heat from 7 to 1. Now this is actually a regenerative regenerative vapor power cycle using one open feed water heater. Now let's refer to a TS diagram over here. So let's say at state number 1, we have got a superheated steam, and at superheated steam, it is expanded to state number 2. When it is expanded at state number 2, some of the steam, as we said earlier, is bleeded out, and rest of the steam is expanded to state number 3. So we are having steam which is expanded from state 1 to 2. Some of the steam is bleeded out state number 2, and the rest of the steam is expanded to state number 3. Now at state number 3, the steam is directed to the condenser, where it is condensed to state number 4 to a saturated liquid. So we are at the inlet of the pump now. So now from 4 to 5, the steam is compressed, and steam is compressed to a exit pressure which is actually higher than the 4 now. Now 5 at state 5 and state number 2 is over here at the inlet of the open feed water heater. Now the steam which is bleeded out at state number 2 is mixed with the feed water which is coming from state number 5. Now the steam will transfer its heat to the feed water. The temperature at 5 will increase, while the phase of the steam will actually change from the steam towards the liquid. So that means like the temperature at 5 will increase, while the phase from 2 to 6 will actually convert from the steam towards the liquid. So heat is transferred from 2 to 6, while temperature is increased from 5 to 6 now. So at the exit of the feed water heater, we would be having a saturated liquid. So now we have got a saturated liquid over here. So now this saturated liquid is pumped from 6 to 7, and at 7 we are at the inlet of the boiler, and at the inlet of the boiler or in the boiler we would be transferring the heat from 7 to 1 now. So that's what actually the regeneration TS diagram would be. Now, if you can imagine, like without regeneration, if you can imagine, we would be transferring heat at state number 5. While in the regeneration cycle, we are transferring heat at state number 7. So if you can imagine, the average temperature at which the heat is transferred in the regeneration cycle is improved now. Now there would be actually a little bit possibility of discussion, or there will be actually a little bit, I would say, like discussion about this regeneration cycle, that we have lost some of the steam at state number 2. So obviously, if we have lost some of the steam at state number 2, there will be reduced power from 2 to 3. That means like steam was reduced, that's why the power would be reduced as well. But it is what actually this a negative outcome of the regeneration power cycle is. While in other words, we have increased the temperature from 5 to 7. This is the positive outcome of the regeneration power cycle. So in practical, the operating conditions are such that the reduction in heat added more than the offset the decrease in the network developed. That means like if we are reducing heat, sorry, if we are reducing work done, that is that is less than the heat reduction benefits. So that means like resulting in the increased thermal efficiency of the regenerative power, vapor power cycle. Now going towards the total mass and energy balance. Obviously, if we are looking for the thermal efficiency in terms of thermal efficiency in real term, so we will be talking about the energy and mass flow rate. So let's start with the mass flow rate itself. So first thing first, like find the thermal efficiency of the power cycle. We need to find the mass flowing as well, or in other words, what we need to say like the energy which would be definitely flowing with the mass. So let me balance the mass first, so that if I'm just looking at the boiler or control volume around the boiler, sorry, a control volume around the turbine. So mass, let's say mass M1 is entering into the turbine. Let's say mass M2 is bleeded out from the first stage, after the first stage of the turbine, and mass M3 is expanding into the second stage of the turbine. So in other words, if I'm saying like what would be the mass balance, so that would be M1 would be equal to M2 plus 3. So that's what actually we could say like this is what we got it at the mass balance. So let me divide this total mass, the total equation with M1, which is the total mass entering into the total mass of the system itself, or even the mass entering into the turbine. So let's say like if I divide with M1, so that will be M1 divided by M1, so 1, and that would be M1, and that would be, sorry, M1 as well. So that means like 1 equal to M2 divided by M1 plus M3 divided by M1. So now, as we were discussing the regenerative power cycle, we were saying like there is actually a fraction of mass which is bleeded out. So that means like if I'm saying like M2 by M1, so in this is the word which we would be calling at, or this is the thing which we call it as the fraction of the total mass M2 by M1. This is the fraction of the total mass bleeded out. So that means like if I'm saying like some of the mass is bleeded out from stage 2, or in other words, fraction of the mass bleeded out at stage 2, that means like that would be M2 by M1. So let me call this fraction, another word which mean like 1 would be equal to, and let me call this fraction as Y, and that is plus M3 by M1. I'm sorry for that. That is, so that means like if I'm saying like M1 mass is entering, so there will be a fraction of mass Y would be bleeded out at state number 2. Now that leave us at M3 by M1, which is left at state number 3. So that means like that would be 1 minus Y. So in other words, mass total mass 1 is entering at state 1. Fraction of the mass Y is taken out at state 2, and the rest of the mass 1 minus Y is expended at expended in the second stage of the turbine. Now let me balance the whole cycle. Now this mass, which is 1 minus Y, will be condensed. So we have got 1 minus Y over here as well. At state 4, it will be compressed. So we have got 1 minus Y over here as well at state number 5. So we are having Y from state number 2 and 1 minus Y from state number 5. So at the exit of 6, we will be having the total mass. So this is what we call it as the mass balance of the whole cycle, or mass balance of the whole regenerative cycle. So in that case, the total mass of the system is conserved. The total mass is already conserved now. Now let's talk about the energy itself, or let's have an energy balance of the system. Uh, let's say like we have only added uh, one feed water heater into the system, and that is at state number uh, 2, inlet from state number 2, sorry, inlet from state number 5, and in exit from the state number 6. So let's balance this now. So having a control volume around the feed water heater. So if I'm balancing this, the energy balance of the open feed water heater, and ignoring the kinetic and potential energy, so that would be, if I would say like, there would be energy which is coming at state number 2, that would be energy Y H2. There would be energy which would be coming at state number 5, that would be plus 1 minus Y H5, and there would be energy which would be leaving at state number 6. That should be equal to what I'm saying, like the energy which is entering into the open feed water heater should be equal to energy which is leaving the open feed water heater. So that means at state number 2, the energy would be entering as YH2. At state number 5, energy would be entering at 1 minus 5, 1 minus 5 H5. That should be equal to 1, which was the total, and H6. So that is the energy balance of the system. Now solving for Y, so that is 0 is equal to YH2 plus 1 minus YH5 minus H6. So solving for Y, we would be having an equation, and that equation would be equal to Y is equal to H6 minus H5 divided by H2 minus H5. Make sure you always try to balance the energy and mass, even if you're solving it in your exam. Please do not try to remember this kind of equation. Just always try to derive this kind of equation. Now we have already defined energy, and that is in terms of Y. We can now proceed towards the finding the power of the turbine, and net power of the cycle as well, and also the pump work as well. So let's say like, if I'm saying like the net power of the turbine, so there would be two power in a turbine. One would be from state 1 to state 2, and one would be from 2 to 3. So that is in a first stage, and thus the 2 to 3 is in a second stage. But if you remember, like from when we were expanding from state 1 to state 2, that was with the total mass, that was total 1. At state 2, we bleeded some of the mass, so that means like when we are expanding from state 2 to 3, the mass is reduced, and that is 1 minus Y mass. So we would be expanding from 2 to 3 in a reduced mass. So there would be definitely some effect of on a work done of the turbine. So work done of the turbine would be H1 minus H2, that is expanding in the first stage, and 1 minus Y, H2 minus H3. So that is expanding, the second stage is expanding in a reduced mass. Similarly, there would be a pump work as well. So the first pump work is from 4 to 5. So first pump work is from 4 to 5. And if you remember, that is with the reduced mass. That is 1 minus Y. And in the second pump work, which is from 6 to 1. So at 6, we have got total energy, total mass, sorry. So that we mean like there would be a pump work from the on the total mass of the system, total mass in the system. So pump work from 6 to 7 is the total enthalpy, while pump work from 4 to 5, that was with the reduced mass, that is 1 minus Y. Similarly, there is actually Q in, and that Q in is from state 1 to state number 7 to 1 in a turbine, and there was a heat transfer out of the system, and that heat transfer was from 3 to 4, 3 to 4, and that was 3 to 4 with the reduced mass. So 3 to 4 is it with the reduced mass. This is the total energy balance of the regenerative power cycle with one open feed water heater. So now if you can like having multiple open feed water heater, you can solve the this thing with the same method. Now let's move to the closed feed water heater. So as the name suggests, and talk about it earlier as well, in a closed feed water heater, there will be no mixing of steam and feed water in a feed water heater itself. So there will be only and only heat transfer from the steam to the feed water rather than mixing the feed water itself, um, mixing with the feed water itself. That means like as we said in over here, there would be same pressure at state number 2, same pressure at state number 5, and same pressure at state number 6. So that means like the total heat transfer in an open feed water heater is at a constant pressure, in which at the pressure at 2, the pressure at 5, and the pressure at 6 are constant, or same, sorry. Um, while in closed feed water heater, if we are talking about, the closed feed water heater does not, as it is closed and there is no mixing of the steam. So these can be, they can be at a different pressure. Uh, just looking at the schematic, if I would say like uh, there is actually extraction steam. Let's say from the previous diagram, it is coming from state 2, and we are having a feed water, let's say at state number 5. So in a previous case, this steam from 2 and feed water from 5 was mixing, while in closed feed water heater, so steam is coming from 2 while water is coming in a closed channel in from 5. Rather than mixing, the steam is transferring its energy to 5, while at 6, let's say, the temperature is increased, while at other exit, the steam which was coming from 2, it is now has transferred heat now, and it is condensed at this point, let's say state 7. Now, so that means like the heat is transferred from 2 to 7 towards 5 to 6, in which the temperature at 6 increase and the phase of the steam is changed from steam towards the liquid from 2 to 7. Now we have got the condensate in the feed water heater now, closed feed water heater. So that condensate I can either be cascaded backward to join the total mass, or either it would be pumped forward, feed forward to to mix with the feed water over here as well. So there are two methods of dealing with this condensate over here. Either you have to cascade it backward, or either you have to pump feed forward. So cascaded backward and feed forward system. So in a diagram like over here, two different scheme for removing the condensate from the closed feed water heater. Um, either you have to pump forward, or either you have to put a trap, which mean like you have to the expand it in a trap, and then put it in the lower pressure. For the pump, it is actually put it at the higher pressure. Let's have a look at the schematic diagram of a of a closed feed water heater. So in this regenerative power cycle, we have got one closed feed water heater. In the same manner, let's look at the schematic diagram. Uh, steam would enter at state 1, and it would be expanded in a first stage of the turbine. Some of the steam, now we call it as Y, is bleeded out at state 1, state 2, and the rest of the steam, which is 1 minus Y, will be expanded in the second stage of the turbine. This steam 1 minus Y would be actually passing through the condenser and exit at state number 4, while would be pumped at state number 5 to the, the pressure, which would be higher uh, higher from the 4 anyway. Now, as in the previous case, we were trying to mix the steam which is coming from state number 2 with this with the feed water which was coming from state number 5. Now over here, it is not actually mixed, but steam itself is passing through a heat exchanger, and only the heat is transferred from 5 to 6 now. While when it transferred the heat at state number when it transferred the heat, the steams transferred the heat uh, from 5 to 6, it itself is condensed now. Now, when it is condensed now, this feed water itself is taken out at 7, and it is actually expended in a throttle, or we call it as a trap. So expended in a throttle or trap at state number 8 now. Now when it is expended in a throttle or trap, the pressure of the steam is reduced now. Pressure of the condensate is reduced now. The phase has already been changed from steam towards liquid. Now at 8, we are now shifting this condensate towards the condenser now. So that means like what actually we have got Y coming from 2 is actually mixed in a condenser, and from in a condenser there is reduced steam coming, and that is 1 minus Y now. Now mixing this 1 minus Y with this Y, so at the exit of the condenser we will be having total mass 1 over here. So now once we have got 1 over here, the total mass is compressed or pumped as state number 5. Now from 5, the heat is transferred from the steam to 6, the temperature is getting higher, and from 6 actually we are putting that feed water in a steam generator to produce the steam for state number 1. Looking at the TS diagram, it will be a little bit easy to understand. So what we have got over here, we are expanding the steam from state number 1 to 2, the total steam over here. At state number 2, some of the steam is bleeded out, which is Y over here, and the rest of the steam is expanded into second stage of the turbine, which is somewhere here now. At state number 3, the steam is sent to the condenser, where it is condensed to saturated liquid at state number 4. Now at 4, we are compressing it to in a isentropic compression in state number 5, and here where our feed water heater is placed. So our feed water is placed at 5, and from the other end it is actually placed at. Now what we have got over here, the heat is transferred from 5 to 6, in which the temperature of the feed water is increased. So from 5 to 6, the temperature of the feed water would be increased. So we have got higher temperature at the exit of the feed water. While from 2 to 7, heat is transferred into the feed water, and the phase of the steam is changed from 2 to 7. So that means like when we are actually having a steam at 2. Now from 2 to 7, which is inside the feed water heater, the phase would be changed. So from 2 to 7, there is a heat transfer in which the phase is changed. And that heat transfer is actually utilized by in 5 to 6, in which the temperature will be right. Now at number 7, we have got the condensate over here. Condensate mean like we have got a saturated liquid over here. Now that saturated liquid can either be feed forwarded, in other words, either be pressurized, so we can put into this higher pressure line over here. So you can imagine like over here we have got a liquid water, liquid. So this was our reduced pressure, while over here from 4 to 5 we have already increased the pressure. So now if I'm saying like we have got a steam, sorry, a feed water at 6, which is at higher pressure. Now if you want to put this saturated liquid in a feed water line, you have to increase the pressure. This is called as feed forwarding system when we are using the pump to increase the pressure to put it in a forward line. While there is another method, what we call it as the expansion through a throttle valve. Expanding through a throttle valve would mean like we are expanding from state number 1 and it would be expanded to state number 8 now. Now, the pressure at 8 is the same pressure which is at state number 3, which is the condenser. So that means like from 7 to 8, we are having a throttling process by reducing the pressure of the 7 to a pressure at 8, which is the condenser pressure. Now from 8, we will be putting that condensate back, or the, the condensed water which was in the feed water heater back into the condenser, and from here it was 1 minus y coming up, and from 7 to 8 it was y over here, and when we are exiting at 4 we have the total mass which is at 1. So this is what we call it as the closed feed water heat. Now for the same, in the same manner, we would be balancing our feed water heater and balancing like this. So there is actually the y H2 minus H7. If I say like H2 minus H7 is the heat transfer in from the steam to the feed water heater from 2 to 7, and that is actually at the reduced mass of y, while there is a heat transfer from 5 to 6, which is at the mass 1, total mass 1. So if you can say like that would be y2 minus y7 at y plus h5 minus h6, that would be equal to 0. Balancing for the y, it will actually give you y is equal to h6 minus h5 divided by h2 minus h5. So in the same manner, you can find the work done of the pump, work done of the turbine, heat transfer in a feed water heater as well, and also the heat out of the system and heat into the boiler. Uh, there are multiple feed water heaters. So the thermal efficiency of the Rankine cycle increase obviously as the result of regeneration. This is because the regeneration raises the average temperature at which heat is added to the steam of the boiler, raising the temperature of the feed water before it enters the boiler. Uh, in many large power plants, if I say like there are as many as 8 feed water heater installed. But as we have discussed earlier, the optimum number of feed water heater is always determined from the economical consideration. We cannot, it cannot be the use of additional feed water heater cannot be justified unless it saves more in fuel cost than its own cost. And obviously, if we have already said about the work done, so if it is saving more in a fuel and not compromising or too much of the work, and obviously not compromising of its own cost, so that obviously there would be justified. So in that case, we can install as many as, like normally in power plant, we can install as many as open feed, 8 feed water heater, and it can be combination of or closed feed water heaters and open feed water heater. Uh, as discussed earlier, the open feed water heater is um, all sometimes used for as a deaerator, removing the trapped air in a cycle. So that's it's sometimes called as deaerator as well, and deaerating open feed water heater as well. Thank you very much. If you have got any question, you can post it into the Google Classroom, and definitely I will be able to answer that one. Have a nice time.